All right, let's get started. It's been a while since I've done a LeetCode question. To be honest, I've been away for a week on a family vacation plus a developer conference, so that's been sort of where I've been. So I apologize for not uploading anything within the week. In any case, let's get back into it. And let's get into our first question, which is binary tree zigzag level order traversal. Given the root of a binary tree, return the zigzag order traversal of the node's values, i.e. from left to right, then right to left for the first level, and alternate between. Okay. I think in this case we can alternate, we can still use a linked list. In the Java implementation, I believe this is a doubly linked list with a head and a tail pointer, which is why we can do this. The idea is that when we are on an even level, go right to left. When we are on an odd level, go left to right. Actually, I think this is backwards. So this should be left to right, and this should be right to left. So layer 0 will be this 3, then layer 1, then layer 2 here. So we go left to right, though there's only 1, then right to left on the first layer, then right to left on the, or left to right on the second layer. This will be just dependent on, so basically we will pop and push elements from different ends of the doubly linked list. We could also use a deck here, a double-ended queue, which would also work. I'm not entirely sure though if the double-ended queue allows for insertion and removal from both ends in constant time. We could actually very quickly check that. So if we use a deck, let's see. Because this is an interface, a linked list is an implementation of a deck. So I think it's fair enough. We could just use the linked list. There is an array deck, but for sure the array deck, if it's using an array implementation, it will not have insertion and removal at both ends in constant time. But it does provide us with the ability to index into it. But in this case, we don't need that. So I think this is a fairly straightforward implementation of the solution. And this will just run in O of n time, where n is the number of nodes in the tree, because we only need to really traverse through them once. And then, let's see, when we decide to go for the space constraint. The space constraint is interesting. Let's see. If we have let's say that we had a node or a tree of height log base 2 of n. Is this O of n squared space? Because n squared is the maximum width of the tree. Assuming that we have a perfect binary tree where where it is both full, so it has all the nodes, both children and complete. I believe it's n squared. I could be wrong though. I'll have to double check this at the end. In any case, I think this is a decent enough solution. And with that, let's get started with the code. So we'll say our deck is going to be a linked list of tree nodes. Add And this is going to be our add first. And we'll add our root. Of course, if we say if our root is null, then we can just return an empty list, which is of type list int. And we can also create our return list here, which will be a mutable list of list int. And in this case, maybe we want to actually instead do something different. And rather than having a deck, then we could use this return list as our deck itself. But a linked list does not implement the list type in Kotlin. And if I remember correctly, this mutable list implementation is using an array list implementation. Let's check out the source. Oh, this is an interface. And this implements a list. And this has an index. If it's indexed inside, then it probably is an array list. And so this won't be very particularly fast. So I think in that case, we are going to keep the deck, though it is very much possible to use the return list on its own and just iterate forwards and backwards within a specific index. We are going to do while deck is not empty. Not sure if this is not empty actually works here. In any case, for let's see, index in 0 to deck.size -1. So we will iterate over, well, actually, let's do a var depth is 0. If depth mod 2 is equal to 0, then we'll do right to left. Otherwise, we'll do for reverse index in deck size -1 down to 0. Iterate in normal order. Iterate in reverse order. And then we will say, we want to create a new list here. So val, we'll call it layer list. This will be a mutable list of int. And for each index, we will say if, so this is normal order, so we will do left to right. So first we will add the item that we are currently in into our list, right? Let me think about this. Yep. So when we actually iterate over the element, that's when we want to actually add it onto our list. So what we will do is that we would do layer list dot add our current index, and this will take in a value. And then let's see, we will say if index.left is not null, then we want to do deck.add last index.left. if index.right is not null, then dec.add last index.right. So this will add it'll go left to right and add the values left to right in terms of the nodes. And this will just go through and remove those items after. We will say here that we want to remove the elements once we are done with them within the deck. So we can do deck.remove first. I think it's remove first. Yeah. Similarly, here we want to do layer list.add index.val. Now we will do left to right. So if index.right is not null, then dec.add last index.right. And similarly, we want to do the same thing, but for the left here. And the entire idea is that we will be iterating through this left to right. Oh, interesting. Let me think about this some more. If we were iterating through this right to left already, we are iterating through this left to right already. And I'm not actually sure if the linked list is iterable. It is iterable. Okay, awesome. Yeah, so if we're already iterating over this layer in reverse order, and then we add the right one, then the left one. I think actually we don't care about this. Let's see. I don't think we actually care about this, in the sense that we still want to do this left to right. For the next layer, right? And in that case, maybe we want to reverse this one. No, because it's already reversed based on our reverse index. Right, so in the case that we want to do that, then we actually, let's see. If we add the right one first, then the left one, that's actually correct. Well, no. We want to add the left one, no, sorry. Because we're adding it right to left. Let's see. Then we don't really want to add it to the... This is a good question, because now that I'm thinking about it, when we add it to the last part, we don't necessarily want to do that. Maybe we want to add first then, which is what we actually want. Yes, and we want to add the right one first, and we want to add it first. Right. Because then we can have the order that we actually want. And then we want to do dec remove last, I think is what we want. Right. Then at the end of this, we want to add our final, we want to add our layer list once we've added all the elements. And then at the end of all of that, we want to return our return list. So the idea is this. we go through each layer left to right or right to left, and we add it in the way that it makes sense for the next layer into our list itself, and as well as into our deck. For left to right, it's the same as before. We still go through and we add it to our last in left to right order, as that is how the level order traversal goes if we are going from a standard left to right. We will also add elements as we traverse through them, as we add their children, and we will remove them from the deck. On the flip side, for a reverse level order traversal, we will do pretty much the opposite. We will traverse the list in reverse order. We will still add the element as we encounter them, but we'll start by adding the right element, then the left element, and rather than adding them to the end of the list, we will add them to the first part of the list, to the head of the list. And finally, we will remove the last element. I'm not sure if Kotlin will allow us to do this, because this is, although this is a for loop, I believe that this is implemented in maybe a little bit of a strange manner. So we might have to do something a little bit different here if we want to actually implement this in this way. In any case, after we traverse through the entire layer, add its children to the deck, and add all of the current layer's items into a list, we will add that list into our list of lists. And then at the end, after we've traversed through everything, we will return that list. Let's go ahead and run it, and let's see if we run into any compiler issues. And let's also see where we're at. So it looks like we ran into an issue with the mutable list. This should be mutable list of, actually. Layer list add, let's see. We will do head is equal to deck.pull first. And then we don't have to worry about this. Right, because head is just an index. And we are really operating this index as more of a counter than anything else. So let's add our actual parameters. And actually get our values from the head and the tail of our list. And let's go ahead and see if there are any other issues. Let's see. Looks like our first and third layers are correct. Our last layer, however, is not. Let's see why. We could still do this. Index in 0 to deck size -1. And we could probably merge these together a little bit more. Because our deck is mostly a counter, we don't really care about whether it's going back in normal order or reverse order. Since the counter the index is just a counter, a normal left to right traversal or for loop is fine. What is not right here, I guess, is this. Let's see. If we add the left element first, then we add the right element here, then our queue should be like that. Should have 9 and 10. And then our tail should be 20 first before 9. I'm not sure why. We're not iterating depth. Depth is equal to depth plus 1 mod 2. And that should give us the result that we want because we were actually iterating depth. Yeah. Let's go ahead and toss in a couple of other cases. So we just forgot to actually increment our depth. You could also just increment depth by 1, but adding mod 2 makes it so it's constrained between 0 and 1, which is really what we want. We could also use a Boolean value for this instead, which would effectively do the same thing. And it might be a little bit faster because it's just a strict Boolean value. And we can actually do that. So we could do var left to right is equal to true. And if left to right is equal to true, and here we can do left to right is equal to not left to right. And this should be functionally the same thing. There you go. Let's go ahead and toss in a submit. Again, we could probably compress this a little bit more actually. So let's go ahead and do that before we submit. So let's do for what this will be replaced by is this. So for index in 0 to dec size -1. If left to right is true, otherwise, head, and this will essentially be moved up here. And this will also be moved up here. And since the for loop is mostly a counter, it doesn't really matter that it's like that. And this should run effectively the same thing. It's just a little bit more concise because we're not running, we don't repeat that for loop there. Like I said, this return list is, or this deck is a little bit unnecessary because we could be using the layer from before. And, let me think about this right now. Is there a way that we could do that instead within the confines of effectively we would be doing left to right, or we'd be reading the reverse of each one and adding that. Okay. But how do we know when to stop? Knowing when to stop would require, I think, a counter that, or a Boolean that effectively says whether or not we've added any children elements. The problem is that in that case we would add an additional layer to iterate over. So what I mean by that is that, let's say that we go, so for each layer within our return list, starting with the root, read the layer in left or in reverse order, no matter what, and add the elements accordingly, or according to the left to right Boolean. So the idea is that we read the list in reverse order, or the next layer down in reverse order every time because we are reversing it every layer. And we will have to add the elements accordingly, right? The problem here is that until we reach the last layer and add no other nodes from the next layer, we don't know when to stop, right? And not knowing when to stop means that we need to add an additional, we add more calls to the left, or we add more calls to well, we just add one layer. Versus here, I mean, are we doing that call anyways? To a certain extent, yes, within this situation, because we still check whether or not the left and the right are null, and then we add nodes based on that. So let me think if this is actually like that much worse. I don't think it's actually that bad. So that's what I'm going to actually do. I'm going to sort of take this chunk right here and say that that probably works. And let's move it up here. So working solution 1 in O of n time O of n squared space. Again, not sure about this O of n squared space, but I assume that's somewhere in that ballpark. This mutable list will start with a list that contains an integer. I just realized that we don't have access to the nodes. We only have access to the integers. Well then. Could we... We could probably reduce it. So if we started off with the tree node, which included the root, and let's turn this into a tree node list. Map from tree node to integer for each element within the list. So this will rely on transforming each value from one to another. I don't think it's associate. I think it's just map, like lowercase m map. Maybe it's, I don't think it's flat map. Single list of elements being on each element of, okay, no, it's not. I think it's just map. Yeah. And we'll probably need a inside map as well. It'll be a little bit weird. But in any case, let's go ahead and do that then. So we can say return list. Well, we actually have to do this in reverse order, right? And we need a var index. We'll call this depth. And we'll say while return or depth is less than return list.size, we can say depth plus plus. And this time we can just do like if the depth mod 2 is equal to 0 and not increment it mod 2, because we need the depth in order to sort of hit our endpoint of our traversal. So we'll say, let's see, for reverse index from return list.get, and we'll say val list is equal to return list at get depth. Down to 0. So traverse all layers in reverse order. Well, do we want to do reverse order for all of them? That's a good question. Let's see. Certainly we'll need a new layer list. And let's see. Actually, I think what we want to do is a very similar thing to what we did before, where, let's see, where we add each element, or where we use the for loop as mostly as a counter. And in that case, what we could do is that we could do list.forEach node. We can say if depth mod 2 is 0, otherwise. If depth mod 2 is equal to 0, then we want to do right to left. If we want to do that right, let me think about this some more. If we did this right to left on the first layer, left to right, then we wanted to do right to left there. Well, then we want to do for each element from the end to the beginning on even one. So iterate over the layer right to left for the next layer. Then iterate over the layer left to right for the next layer. And this will be, in this case, if we did 20 and 9, then we kind of want to do reverse order as well. This is reverse order. Because we want to start with the last element and add them right to left. And here, because the elements are already reversed, we want to add them in reverse order right to left as well. Okay, so in that case, we can do this for index in list dot size down to 0. This should be list size -1. Sorry for jumping around with the logic and everything. We want to say if, well, val current node is equal to our list get at index. Then if index dot right is not null, then we want to do new layer list add index dot right, and similarly for index dot left. And the idea is that if we are starting here, we are starting from the last element. Let's see, that adds items on the right to left. I wonder if you allow for an add operation at a specified index. Oops, did not mean to close out that tab. Let's see. And it's add at index. And I believe we want to add these at the head of the, and we want to go left to right order. No, right to left, yeah. Then in that case, do we want to add these at the end in the same order? I think we want to go left first, then right. So this is effectively what we did before. And we kind of want to flip this, right? Because, let's say if list is not empty, or if new layer list is not empty, then we want to add it to our return list. And increase our depth. So we start off with our root. Then we go through each element in reverse order. Since depth starts at 0, we will start with the left candidate and add 9. Then we go with our right candidate, which is 20. And we add that into our list, which is not quite what we want. We want to add right then left, right? So we want to add right, so that's the 20 for our next layer. Then we add 9 to our list, right. Then in the next one, we have 20 and 9. Our depth is now 1. So now we go in reverse order. So now we start with 9 first, and we go to the next iteration where we add our right element to our head first. Well, 9 has nothing, so we go to 20. At 20, we will add our 7 first to the head of the list. Then we add our 15 to the head of the list, because our 7 is on the right and our 15 is on the left. We add 15 to the list, or the 15, comma 7 to our list, and then we continue our depth. At this point, our depth is equal to our return list size, and at that point we return at the bottom. So I think this is what we want. And now we need to do a map function, and this will be a internal list, which is a list of tree nodes. And we just want to return the item value. So this returns a list of integers. And then subsequently, this returns a list of integers. And let's go ahead and run this, and let's see where we end up. Let's see. Type mismatch. We know that this is a mutable list of list tree node. Oh, this should be a list of. And this index, again, we should be using current node, not index. So this is a more Kotlin-y answer, I feel, but I don't think it's necessarily anything quicker. At the very least, this returns a runtime, same as above solution, but runs in O of 1 space because we're reusing the list that we're using to return. Although you can argue that this is realistically a bit slower because we need to run the map function to transform each node into its integer form at the end, which will require another pass through n nodes. So it seems like it works for this case. Let's go ahead and submit and let's see if there are any issues or where we're at. Looks like we ran into an issue here with this tree. Let's take a look at what it looks like. Okay, that's what it looks like, and we want it to return 13245. And we're running into 13254. Interesting. Let's see. We add 1 into our node, or into our list. Then depth is at 0, so we go this route. We add the right node, in which is 3. Then we add the left node, which is 2. So we push in 3, 2. Then we go in reverse order again. So now we go to 2. We start with 2. 2 will add in 4. 2 will add in 4. However, when 3 comes around, because that's the next element in the reverse order, it will add 5 in its place, and it will add that 5 at the head. I see. Okay. So if we're doing that in reverse order, do we need to do this at all? Let's see, what happens if we add in our values in the standard order? If we added our right side, or our left side, in this case we'll just add our 4. Then in the next case we'll add our 5. And that's perfectly fine. So do we even need this? Let me just double check with this. If we go through 9 first, then 20. 20 we will add our right value first, so our 7. Then we will add our 15. Assuming that we go this route. So this will go, if we wanted to do that, that would be 3, 29, and since we go in reverse order, 9 doesn't add anything, but 20, we will add our right value first, so 7, and then 15. Maybe the play here is not to add it to our head, but instead just add it to the end, but add it in the other order. Let's see if that works for this one. Well, since this only has one child, it won't affect it that much. Let's add another child for you. So let's add a 7 there. So what does this look like? So we have 1, then 2, 3. So 1 is nothing special. So then 3, 2. Then let's see what happens at 3, 2. Well, we start with 2, and 2 will first add its left child, then its right child. So it'll add 4, then 7. And then 3, which is next, will then add 5, which is precisely what we want, right? Right. Okay. Let's just double check and remove this and return this back to its original state. And let's also run the example test cases. Oop. Just ran a blank test case. Let's use example test cases and let's add in the one that we failed on. So yeah, going back and forth in reverse zigzag order can be a little bit confusing if you don't really keep track of it. In any case, looks like it passed. It's a little bit slow on the slow side. Again, this is more of a trading space for time, whereas this initially was more of a trading time or trading space for a little bit better of time. But in any case, both of these solutions work. It just really depends on whether or not you value the space consumption more or the time consumption more. Because this one can get it done in one pass, and this requires 2, mainly because of just mapping it. And there's no way really around it because it requires you to return a list of integers rather than a list of tree nodes. But in any case, I hope you learned something, and I'll see you for the next problem.